Okay, so this semester we're going to cover together ECE 302 and sorry, this is antennas and propagation. And we've taken courses before, so there is no need to detail who I am. We've taken together two courses. And in fact, these two courses that we've taken together, the electromagnetic field theory and the electromagnetic wave, they are the course prerequisites for the class of antennas and propagation, which means that you have to have a good, acceptable knowledge of calculus, of vector calculus, and also the good knowledge on some applications of differential equations, because the differential equations, we need those for the boundary value problems whenever we want to calculate what is the behavior of an electric field between two certain boundaries, between two certain physical boundaries, where we know the value of the electric field at these two respective boundaries. Okay, so we need to know, as we said, vector calculus, electromagnetic wave basis. So we have to understand, for example, that the wave, it does propagate in space and in time through the propagation is shown using the propagation factors that we often use to consider those as e to the power ikx or e to the power I omega t, where the second one is the propagation in time. The first one was a propagation in space. And with that I, we just mean that we're talking about this is a complex numbers. So it's good also to know, to have some basis on regarding the complex numbers, such as where z is equal to a plus ib, because the complex number, whenever we see it, we consider that we are dealing with a phase change. Okay, as something is propagating in any dimension, we can observe a phase change, because the sources that we are going to see in antennas, or that at least we have seen even in electromagnetic waves, they had a phase. Okay, so the relative quantities, they don't always meet the peak voltage and the peak current at the same time. For example, regarding when we did from the course of electromagnetic wave, what you could remember, you might remember that the impedance, this was a complex number. So we had an amplitude times e to the power phi theta. Okay, so this was a delay. So a delay between the phase of the electric field and of the magnetic field when we had the binary or the dual component for the electromagnetic wave. Now, this concept that we have seen, which used to be the ratio between the magnetic field, the electric field and the magnetic field, we're going to see something, an equivalent principle, also when we deal with antennas. So this is just a reminder of this is what we are going to see. And in this case, this complex number, which is going to include the difference between the amplitudes of two quantities, and also the phase difference between these two quantities, where the phase difference represents how much later in time something is going to happen. And this later in time, we should always remember that the later in time means the following: whenever t is equal to a full period, this is equivalent to a length scale which is equal to lambda. Okay, and the phase, so this is equivalence, and this is equivalent to dealing with a phase which is equal to 2 pi. So these are so when you say that we have a phase difference between two different variables, we're talking about this angle or this value, which is measured in radians, and there is a linear relationship between how much length of the wave has propagated and how much time out of the full period, where the capital T is the period. The lambda is the wavelength, which is measured in meters. Phase is in radians, and as we have often try to stress in this course, we've said that the first essential component that is very important is the dimensional analysis. And in this case, we should remember that the time is measured in seconds, the length scale is measured in meters, and the phase angle it is measured in radians, which in principle it is no unit. Okay, so this is in radians. So this is where we are going to see the equivalence of the intrinsic impedance in the waves. We're going to see it here as simply the impedance, but we're going to see how we deal with it. I just want you to remember that we will have to deal with the complex numbers. So simple algebraic operations between the complex numbers, it's good to, we're going to use those. And other than this, it is always strongly suggested that for the courses that you have taken before, including electromagnetic field theory and the electromagnetic waves, you had often included, you were asked or you needed to fill a cheat sheet or a formula sheet where you had several relationships. And in this course, we're not asking to memorize all the relationships. You should definitely be able to understand once you see those and to conduct the dimensional analysis, because if the dimension analysis does not match, does not fit, that means that you should go and fix the equation that you have at hand or that you might be dealing with. So this is, how can I say, the short overview of what is the prerequisite information or what you need to know before you take this course. So far, you have taken all the relevant information that you need to take. So just reviewing those, or you should be comfortable that you have acquired this knowledge in the previous courses. Now, for this course, the textbook that we're going to use, it is actually we can track textbooks by the author. So we're going to use the book by Balanis. And the title of the book, I sometimes, let me check, I have it here on Amazon, so I can send you the link. Balanis Antenna Theory. It's really a good one. I can share with you the link, so you can follow it up. And this book, you can find this one also in the library, so you can borrow whenever, if you want to borrow. Okay, so this is the textbook by Balanis, and let me check what was the complete title. Of course, antenna is in the title: Antenna Theory, Analysis, and Design. Okay, so this is the book that we are going to follow. Also, the lecture notes that I shared with you on Google Classroom or on the online platform, it is based, at least the didactic structure, how the topics are ordered, it is based on the book by Balanis. Now, other important information is the separation of the grade. So in this class, we're going to have around, for homeworks, we are going to expect a 10% grade. Okay. Now, the number of homeworks traditionally might be 2, it can even be 3 or 4, but all of them in total will have 10%. And if you get any the quizzes, you are going to expect quiz, which is going to be another 10%. So far you have the 20%. Then midterm, you're going to have a 35%, and the final exam, it's going to be 45%. So this would be a total of 100%. And if you ever receive any extra homework or any extra assignment, that will count for more than 100 points. So the course could be graded over 100, over more than 100 total points. Okay, so this is the grade distribution. If you have other questions, we can communicate during the semester. But now, in order to continue, let me see just for a second. And actually, let me see. share this. Okay, so we're going to discuss the antennas, and initially we want to talk about the introduction of antennas, the types, and also an essential element is also the radiation mechanism, then the current distribution on thin wire antennas, and how the antennas have developed. Actually, before discussing I might need to jump sometimes between the slides and the notes on the board, and that's what we exactly will have to do. And regarding this, first of all, regarding antennas, if we understand antennas, we're going to understand the common discussions regarding such as the fourth generation of wireless communication, the fifth generation of wireless communication, and what is observed is that if we check, in fact, if we check as a function of time, probably we can, well, we can stop sharing just for a moment. Let's do this. Stop presenting. So there is an interesting observation that is done, because antennas, as we commonly know, is that they are used for communication, and whenever we use a specific frequency for a specific purpose, what happens is that once that frequency is allocated, we cannot use it for many other purposes. Okay, so it has a certain frequency range, and what is observed as a function of time is that as a function of time, we observe that the frequencies employed or frequencies used, they have always been increasing. Okay, so there is always an increasing trend between the frequency that we have used. Okay, so you might observe such a relationship. Then we can also draw another axis, which is the bandwidth used, and we observe that also the bandwidth that is used is also an increasing pattern as a function of time. Okay, let's draw this with two different colors. So they both increase. Okay, of course we have beautiful graphs that exactly show the scale to what bandwidth and what frequency we are currently operating with. But in 2021, we are just we're trying to successfully pass from the fourth generation of wireless communication to the fifth generation. And for example, the fifth generation, it operates in the order of 30 gigahertz. It has two different ranges where it operates. It has sub 6 gigahertz frequency that can be used for communication. If it is actually sub 6 gigahertz, since it is very close to the 5G communication wireless networks, sometimes it might be confused that 5G, which is the fifth generation, it might correspond to 5 gigahertz. It's just a coincidence. So there's the first range that the fifth generation communication frequencies operate with. Then we have also the second range, which is something between 25 to 50 gigahertz. So, there is also, actually, there is similar to the Moore's law. You know, there is a Moore's law which states that as a function of time, the number of transistors that can be allocated per certain volume is going to continuously double or increase in time as a function of time. Similarly, there was a law, Edholm's law, which states that the bandwidth of new wireless systems that we develop, it doubles every 1.5 years. So it looks like during a bachelor study program, from the first year to the third year, you might see a doubling, not a doubling, you see 4 times higher bandwidth since you started the first year. Now it has multiplied by 4, and you know that something which continuously increases by a factor of 2, or any factor of number k, that is similar to an exponential increase. Okay, so these are, and the antennas, in fact, they have several applications where the most important applications is simply communication, the wireless communication. Then the second other application is the satellite communication. We can use radar communication. It can also be used small antennas, which can be used also for medical reasons, which can be even wearable antennas. And currently, in fact, there is a very hot topic of research where several specialists in the field, they have transformed their research areas, or they have adapted to implementing antennas for medical purposes. And always when you do something for medical purposes, it has a higher impact in terms of, at least it has a higher impact both for the improving the quality of life, but it has an impact for the productivity of the professors, and also for the training of the students that work with these professors in the universities or research centers. And regarding the medical applications, what it can be done is that there can be some small wearable antennas which can be attached like a patch, similar to a patch. And patch antennas is a specific family of antennas. And what they can do is that they can generate with a specific direction certain frequencies, and they might cause increase of temperature in a certain region. So this could be considered as a treatment for cancer cells. So you can apply a heat at a very well-localized region in a biological system. And so this is the application of these medical applications, which requires actually an array of little antennas in order to enable this. Another important, interesting topic that can be where the antennas are used is the radio astronomy, where they operate at a very high frequency. So they operate actually up to 100 to 500 gigahertz. That's the upper limit for the radio astronomy applications where the antennas are used. Now, regarding before I go into the slides, because I might need to use something on the board, is that the antenna is in fact, it's just whenever we discuss antennas, there should be always, we're going to mention twice, two times the discussion on the transmission lines. We have to talk now, just at least to give the rough definition of why transmission lines, or understanding that transmission lines are important right now. But we might see them in the future, after a couple of weeks. We might cover again some examples on transmission lines. Now, the antenna, so normally, in order for us to operate with an antenna, of course, let's say we may be interested to transmit a signal, okay? So we need to have a source of excitation, let's call it this way, because, for example, if you have a power supply like this, and we ground one side, this is nothing, okay? But if you ground a signal, something like this, but here you have an alternating current, this is an antenna. So the simplest this drawing, or the simplest understanding that we could associate with an antenna, this is it. So we just have we ground the signal, we have a power supplier which is going to produce a current, because we know that currents, because since we have here electric and magnetic waves, which are going to propagate through a vector k. So this is the propagation direction k. So we want to have the E and B, and we know that the electric field B, I mean the magnetic field. So these are as a product of the charge. So E is produced by a point charge, and magnetic field is produced by a current. Okay, but in this case, we know this one. Okay, so from the early stages, since when you were a bachelor student or when you were a freshman student in the first year, in physics 2, or when you did electromagnetism, you remember that you said that you have a point charge, you create an electric field, but you have a current, you immediately have a magnetic field. But now in the wave, in the antenna theory, what we don't want only a charge. We want a charge that can be accelerated or that moves as a function of time. Okay, this is something essential. We should not forget this. And for this reason, a constraint like this, it does nothing. Okay, you have grounded this is 5-volt power supply, you measure 5 volts, that's it. But at the same time, if we have a wire here, a single wire, this wire can be a coaxial cable, it can be a single wire, a very thin wire, it can be a conductive material, which would mean that the current is going to lay on the outer boundary of the wire. It can be also something which is not a perfect conductor, which means that the charge can be allocated over the whole volume of the wire. So it could be anything, okay, or it could be any family of the antenna material, and all of these can produce a signal which can be picked up later on, okay. And picking up a signal or an antenna or a wave, the simplest thing that you can experiment in a lab would be, let me try to figure out some components. If I can see anything in a minute, I'll bring it to you. Okay, so I found something. Anyway, so this is one antenna. The first, well, this is not an antenna which is going to transmit a signal, but this is an antenna which can pick up a signal, now to receive a signal. And the simplest way to do it is the following. So here we have an oscilloscope with, I'm trying to read the frequency, 16 megahertz, 1 gigasample per second. Okay, I think we have better, slightly better than these. But normally this just picks up a signal. And the receiver part is going to be, so you just need to plug this one using the DSC cable, that's it. And then here is your receiver. Okay, you just need 2 conductors that are, you need to have this. Okay, this is a reception. You can change, so you can have these 2 metal pieces. You keep them here, you pick up a signal. Then you make them further and further, you pick up another signal. So that's your antenna, the simplest thing. You come to the lab, you plug this thing in. You just have a wire like this, and you're going to read something oscillating in the oscilloscope. Of course, now this is off. But this is the simplest way that you can really touch, or you can really feel that you are measuring something, or as a simple application. Okay, so if you see anything which oscillates randomly because you have a wire extending out there, this is because you're picking specific frequencies where the size parameter, or the size of this wire component that is going to pick up the signals, it is comparable to the wavelength of the signal that is coming through. And during the courses that you have taken in the past, I'm sure that the lecturer that taught you, you might have heard several times saying the following statement, that whenever there is a communication between one component and another, the matching in frequency is essential, but also the matching in length scale is also essential. Length scale, which means that you can make up an antenna which is, let's say, which has a certain length scale, let's say 10 centimeters, and this antenna can successfully match with any wavelength which is equal to this size of the physical material, physical component. Okay, so as we're having this discussion, sorry. Okay, so we said that we had these antennas which had to be. They're going to operate. We said it actually. They're going to operate on AC regime, or AC voltage, or alternating voltage, alternating current. Not these. So these don't help much. And in these frequencies that are operating, we need, let's say, this, we can call this one the generating region, or the segment which is going to generate the disturbance. And we call this a disturbance because this is something which, how can I say, it's something that you can see as equivalent, as such that the entropy or disorder in the system keeps increasing, but it keeps increasing for something good. What we mean with this is that as the voltage changes the function of time, we have an oscillation of the charges. The oscillation of the charges, they're going to produce this. This is essential. They're going to produce a quantity which is as a function of time. E is equal to a function of time, which means that if this is the case, we can say that the rate of change of this electric field is different from zero. So if this is different from zero, immediately we know that also we're going to have a B, magnetic field intensity, which is a function of time too. If this is a function of time, the derivative of this is going to produce, so let's call this one E1, B1. Then, since this one is changing as a function of time, we're going to have another electric field E2 as a function of time again, and E2 is going to induce B2 and so on. So the way that antennas are going to operate, often you are going to see drawings like these. So this is going to be the pattern of an electric field. This changing electric field as a function of time is going to produce, this is the magnetic field. We try to draw this one in a different color. This magnetic field is going to produce an electric field, and this beautiful coupling between these two, you might see this often. Okay? And the principle is based on the fact that Maxwell's equations have to be respected, where they state that any rate of change as a function of time, or any different from zero time derivative of the electric field and the magnetic field, will generate subsequently each other. That's why I call this one as a disturbance, which keeps propagating, and they keep generating daughter waves, okay, or sub-waves, which they generate from each other. And we have a specific performance of how well the waves distribute, and how well the signal, and how strong the signal can be at a certain distance, and how much the signal might attenuate depending from because of the properties of a medium. And you know from electromagnetic waves course that you have taken that even waves, they have a certain length of propagation, where the most critical aspect is, for example, there is a parameter which we used to call this one the skin depth. Skin depth, it was defined as the depth into a new material where a wave can propagate up to some percentage, okay, up to 63%, or let's say whenever the power is attenuated by a factor of 63%, that can be defined as the skin depth. Now, skin depth, we traditionally use this one for materials that have a certain level of conductivity, and or when you say certain level of conductivity, we mean this sigma is slightly different from zero. Now, this sigma can be infinitesimally small, but it's different from zero. So that's the, and once we have this, we are going to have some losses in the system, and even air. So in a rainy day, because of the, let's say, because of the water, it behaves slightly, of course, very different from vacuum. And if we consider, for example, the seawater is really a good conductor, which means that it has a limited skin depth, or a limited distance where the wave, in this case, a signal that might be sent from an antenna initially, but before, when we did the electromagnetic waves, we did not discuss too much onto how this wave is constructed. We just used to say often that we can have an antenna, the wave is generated, it might have a spherical geometry because of things cannot be made perfect. But at a very large distance, we often used to say that the wave is going to be considered a plane wave. Okay. So we've seen this one a lot, but we never discussed how this disturbance is produced. Maybe, not maybe, but for sure, the next closest point where we could have had a discussion regarding the generation of the different shapes of waves, it was in the waveguides. So in the waveguides, we have seen, for example, that we have some transverse electric wave, mode 1, mode 2, mode 3, or if you have both waves, you have TE11 or TE21, and these, for example, these are different waves which they behave differently in a certain, whenever they are bounded in a region like a waveguide. And for example, we could have discussed there how can you generate a system which has an oscillatory current inside the waveguide that generates a specific mode. Okay, that was the, how can I say, just so I want to remind you that that kind of discussion could have been done whenever we discuss these plane waves, and then we could discuss how this is generated, that at the far distance it becomes like a wave, plane wave, where every point on this plane wave is at the same phase. So that's how we discuss the simplest mode. And another aspect would be that if we have a waveguide that goes like this, if we want to have, let's say, a specific mode TE13, this has a completely different wave, a different way how it can propagate, but at the same time, it is very different how we can generate these modes inside the waveguide by using, let's say, we can insert a wire in there with a specific oscillation, with a specific configuration of the antenna or of this wire. We can generate this specific mode. Now, the moment that we're discussing here regarding the non-zero conductivity, this is important because these issues, they are very important in the stage where the wave is produced. So normally we have a source, which the simplest source, you can assume this, okay? Source, then there is a transmission line, there is a line which picks up this disturbance, and it tries, so it picks up with this, we are using a disturbance, but it's a source generation. Let's call it not a disturbance. Disturbance has a bad connotation. We love antennas, we use them, they are very useful. They make our life easier, they improve the quality of life. But let's say that we have a source generated, so there is a signal generated, and then we have to pick this signal, carry it over a transmission line, send it to the antenna, and the antenna should make sure that this disturbance is then sent to the free space. Okay, now we have a free wave which can be sent for transmission to be picked up probably by some other component. But so it looks like the stage from the source or from the generator to the free space, there should be some components where the major one. So we can consider these like, so this is the source. Let me draw the source like this, and this source, that's it, okay? Then we need to have a transmission line over which this signal is going to be carried over, okay? And then we're going to have the antenna, and this, the third component, is the antenna, which makes possible that this disturbance for these waves that can be in this region, then this component makes sure that the wave will be sent out to free space. Okay, and now when you see this big picture or this drawing, I want to bring the attention to some concepts that we have seen those, but we have not been very careful. But this is the time to review some aspects out there. And one essential component issue to discuss here is that this can be considered as a different medium, okay? And when we say it's a different medium, this has specific properties. This has a, let's say, impedance Z1. This has an impedance Z2, and this has another impedance Z3. And we are communicating from one region to another, and from the second to the third, and so on. Now, this analysis that we are doing here, we can use circuit theory or circuit analysis. Let me call this one circuit theory. But actually, discussing this in terms of circuit theory, it might be a little counterintuitive. Okay, we don't pick it up very easily. But personally, when I was a student, I used to think that the analysis that we need to do when we see how the signal is generated from region 1, second, and the third, I think that the wave, electromagnetic wave, this we can consider that the knowledge on the electromagnetic wave, it provides enough intuition to understand that if we move from one region to the other, we might have a reflection backwards. Okay, so we are observing a barrier, and this barrier, this is the same way that you might have a wave coming from vacuum. Then you have a region which is, let's say, a piece of glass. And whenever there is a piece of glass, there is a probability that some part of the wave is going to be reflected backwards. Similarly, after this piece of glass, you might have a wave going into water, okay, or into a region. And there we also have a reflection. But now this reflection, it's easy to pick it up from the waves analysis, but it is also very didactic into understanding how the signals propagate. We can also understand this from the circuit theory. And you might have seen this one, because two different circuit components, we know that we can have the maximum signal transmission from component 1 to component 2 whenever we have a matching of the impedances, okay, impedance, which is a unit of equal to ohms. So, so this provides this provides an intuition of how a signal can be reflected backwards. But we can do this also with circuit theory. Now, with the background knowledge that we have from waves analysis, we can say the following. So let me start from the topics which can be as much as intuitive as possible. So let's assume that let's assume the extreme case. Okay, we have a perfect conductor. Sigma is much larger than 1. That's a perfect conductor. What we know is that if we have an incoming incident wave that is coming onto a perfect conductor, we have a perfect reflection backwards. Okay, so this is the K reflected. Then, what happens then is that we have standing waves, right? So this is something that often you might have received this one as a question in the midterm or the final exam of waves, to define what is a standing wave. So a standing wave, it was a wave where the peaks is going to look like this, or this again. So we call this one a standing wave because the position where the waves achieves its peak intensity, it's always constant in time. And also the nodes where the intensity is equal to 0 is also constant in time. But at least we're discussing this one just to remind ourselves the concept of the standing waves. Okay. Now, when we discuss here all the components that start from the generation of the wave to the transmission, since we have here region, let's consider this one region 1, 2, and 3, we will have. First of all, we have a reflection of the signal. Signal hits in here, and some part of the signal will be reflected backwards. Also, a signal comes through the transmission line, and then some part of this will always reflect backwards. We cannot have perfect matching between the impedances between two different components. Okay, so since this is the case, we're going to have a standing wave right here in the transmission line, which makes the connection between the antenna itself and the source where we have generated this initial excitation. Okay, so we're going to have this standing waves, and because we will have a signal which will go forward and also a little back of propagation of the wave in the reverse direction. And the propagation in the reverse direction, based on the knowledge that we have seen in electromagnetic waves, we can often see propagation vectors in the same way, which can be e to the power ikz, and also e to the power minus ikz. The first component, it describes a wave which propagates along the minus z direction, and this one describes a wave which propagates in the positive z direction. So in this case, if we assume that we want to propagate in the positive z in this direction, this describes this wave, and this describes this wave. Now, this is only only the intuitive approach of understanding why the waves in a system that we want to use it for an antenna, how it works. And we need to know this because we want to have not only when we operate with antennas, but in several components where we want to measure something which has a very high sensitivity, we want the impedance mismatch. So these highly sensitive circuit components, they can be used, they are trying to be used in very essential applications, where some of these applications, they even are for national security, or they go for the army, where all the money is thrown into it, and nobody cares about how much money goes into it, so it doesn't even have to be cost effective, but it is very useful, which would be the case of trying to be sensitive to pick up very small signals, or to pick up very small molecules, or and to be selective in these two small molecules. With molecules, this could be something, some material which would be toxic, or it can even be CO2, carbon dioxide or carbon monoxide. Monoxide is more dangerous than dioxide, and we want to have a sensor, and for this sensor, we need to draw a very highly sensitive analog circuit. But for this highly sensitive analog circuit, we should always be aware that we should have an impedance matching between the components of the measurements. Otherwise, you measure nothing. Okay, so you can have a very good idea, but you don't implement carefully the concepts of the zero reflection of the wave from one medium to another. And zero reflection of the wave, what does it mean? This is equivalent to stating that the impedances are the same on both on medium 1 and on medium 2, or on any two subsequent mediums. So we have to understand these. Of course, we can share very interesting publications that are very recent, where they try to use this concept that I just described, and they try to implement it. And always they find, or there is a very big challenge into producing circuits that really have almost zero losses. I mean, at least that's the intention. Now, so this was what the electromagnetic wave teaches us. Now let's see how we can formalize this one in terms of the circuit theory, okay, or how a circuit. So I think let's have a look at how this idea can be constructed based on this. If you like, we can have a short break. Any question for what we did so far? If not, let's give a short break.